Welcome and good morning, everyone. Thank you for joining us for the second in our 4-webinar series on using marine shoreline design guidelines to improve shoreline stabilization permitting today with the topic of site assessments and demonstration of need. And for those of you who were with us last week, welcome back. And if this is your first time joining us, welcome to the webinar series. This is sponsored by the Shoreline and Coastal Planners Group and was developed by Washington Sea Grant, Washington Department of Fish and Wildlife, and Washington Department of Ecology. So first, some logistics. We have disabled participants' microphones, so if you have questions, please type them into that chat box. You should be able to see where that is on your screen, and we've got a picture of that here. And we will be following the chat box and watching for your questions. Also, we have materials that are available for download on the Shoreline Coastal Planners Group website at coastalplanners/webinars.org. And these are important because we will be referencing them during today's webinar. So you can pull them down off of the website, print them out, or copy them and use them to follow along in the webinar. And the materials were also included in the reminder for today's webinar. And just as a reminder, we are recording this. And for those of you who could not join us last week, or for those of us who did join us last week, we've already posted last week's webinar, again, on the Coastal Planners/webinars.org, on that website. We have both the recordings and we have the PowerPoint slides from the presentations with the notes. And just a note on the webinar postings, the recordings, the captions have not been edited. So if you require captioning, we will be fixing those in the near future, but they are not. We wanted to get them up as soon as possible so everybody would have access to them. So today's webinar will cover the key elements of what to look for in a site assessment and how to review a risk assessment. We're then going to discuss the demonstration of need requirements, in this case related to the Shoreline Master Programs, and provide MSDG, that's Marine Shoreline Design Guidelines, based tools that you can use when reviewing a geotechnical report to make sure that it complies with Shoreline Master Program consistency, or for those of you who are not from Washington, you can use it if you require a geotech report. Today, you'll be hearing from 3 speakers. I'll start by introducing myself. I'm Nicole Fagan. I am a coastal management specialist with Washington Sea Grant. Now, let's hear from our other 2 speakers.
Hi, I'm Sydney Fishman, and I'm the Shoreline Armoring Planning Associate at the Washington Department of Ecology.
And I am Corey Morse. I am a habitat engineer for the Washington Department of Fish and Wildlife.
Thank you. We realize not everybody was able to participate in all, and will be able to participate in all of these webinars. And if you weren't able to participate in the first one, we just want to take a minute to take a step back and review what was covered in that first webinar if you couldn't join us. And as a starting point, we want to remind everyone the webinar series is designed to give an introduction to the Marine Shoreline Design Guidelines. It's a tool for understanding how to design and review permits for shoreline stabilization and to do a better job of understanding how to use shoreline soft shore and alternatives to hard armor. So in webinar 1, we introduced some of the basic concepts of our shoreline. We gave an overview of the coastal processes, and we talked about the geology and the biology. And these are all really important key concepts as we now move into how to conduct a site assessment. And if you missed that first webinar, again, you might want to watch that recording of the webinar we've posted on the Shoreline Coastal Planners website. We also then introduced some of the key concepts of Washington state permit process that applies to armor removal, soft shore projects, and the different concepts explained in the Marine Shoreline Design Guidelines. We introduced the three major types of permits typically involved in permitting shoreline stabilization projects in Washington. These are the shoreline permits authorized through shoreline master programs by local governments, the hydraulic project approval, the HPA, that's issued through the Department of Fish and Wildlife, and permitting by the Corps of Engineers, either through a Section 10 or Section 404 process. Now, I'm going to turn it over to Corey, and he's going to walk us through the process of conducting a site assessment. And it's important to understand as much as possible about a site, as this will then let you determine what type of approach or technique you want to consider for that site. Now, please remember that save your questions or use the chat box. We've saved plenty of time at the end for questions. If we feel that we have plenty of time, we will try to take some of the questions as we go along, but we will swoop back, and we're monitoring the chat room so that we will see those questions and get to them. So go ahead and take it away, Corey.
The guidelines cover. All right, can everybody hear me?
Yes, you're good.
All right, cool. I'm gonna go. Let's jump right into site assessment. The guidelines cover site assessment in Chapter 3, and in the next 20 minutes or so, we're gonna cover the first part of that chapter. So, there we go. No offshore discussion, including breach processes, would be complete without a photo of Hugh Shipman describing what's going on. So there's that token photo. To kick off the topic, we're going to cover the functional aspects and application of Chapter 3 of the guidelines, which is titled Site Assessment. So we'll run through the important things to look at your site, some coastal process observations, and how you might make those in the field. So, generally, we're going to kind of follow this checklist that you see here. I'll touch on this a little bit later, or kind of as we go, but this is a tool that you can use as a site assessment reminder list, or you can make copies and kind of have it for use on individual sites. So this actually covers all of the same items that are on the checklist in Chapter 3, just reformatted to be a little bit more readable, and it's got a little bit more common speak language in there. So. Again, should be available in the packet of information we have for download, so you can go ahead and grab that. So let's run through some of these important items that we want to observe and why they're important to a site assessment. So starting off with geology and geomorphology and the site soils. So why do we care to characterize the slope? A big part of the reason for this is to have some idea of how the materials of the slope at risk will potentially behave. And the best way to see what the soils are that make up a slope would be to sample them. So to really get an idea, that's how you get started. Unfortunately, that tends to be kind of expensive, and real in situ information isn't always or even often analyzed. So a lot of times what we're looking at is what's readily visible. So one of the key factors that drives the strength of materials and their ability to kind of stand up in the absence of exterior forces, things like a wall or a revetment, would be that soil's angle of repose. So it's represented typically by a Greek phi. Really, it's just the angle that a pile of loose soil would slope to and be able to kind of hold a load at. It's a helpful characteristic because you can infer some good information just by seeing what does that soil look like. So if you have a big cut slope like you see on the photo on the right there, and it's probably something you kind of experimented with in the sandbox when you were little, piling up sand or dirt or gravel or things like that. So there's lots of empirical values for this, and there's a short list on the slide there. You can, a quick Google search will give you a lot of information. So let's move on to the next item in our checklist. Under the next heading there is layers in the slope. Now, why is it important to observe the layers in a slope? I already touched on the angle of repose with different soils. So if you can see the different soils and layers in a slope, they can fail varyingly in a bluff. The other thing to pay particular attention to is if you say an impervious layer that wouldn't transmit water below a layer that will transmit water. So, you know, a clay or a bedrock layer underlying some gravel or till or sand. The particular concern being that the upper layer will transmit water, which eventually, oh, we're cycling a little quickly there. Can we move back just a touch? There we go. So the issue there is that water will percolate through that pervious layer, hit that impervious layer, and then drain laterally out of the slope. And the result, as you can kind of see in the photo here, is that some of the fines and materials in that upper layer will get carried out along with water, and over time can form a channel that can grow and grow and grow and destabilize the upper layer. So in the photo there, you can actually even see the accumulated fines piling up there, and the kind of the little scarp that's forming over that impervious layer. So since we touched on failures, let's talk about slope failures. So the site assessment, the language is landslides and slope stability. Let's look at how slopes fail, how they can be unstable. There's a lot of ways to characterize slope failure, and depending on who you're talking to, what your expertise happens to be, those might be labeled different ways, but I'm going to stick with 4 particular failure types that you'll see in a moment here as that checklist kind of, there you go, comes off of there. So let's start with those on the left. The top one there is a rotational failure. You might hear an engineer call it a global failure. Global meaning kind of the shape of that semicircular failure plane there. Next on the list is a slide failure, also called a wedge failure. It's really just a wedge that either slides or plops right off of the slope. And then what we see on the bottom of that list is a overhanging slope failure, which is a result of toe erosion in an area that happens to be well vegetated with shallow rooted plants such as grasses or invasives that have really heavy roots for really shallow distance. So these are all failure modes that can happen relatively acutely, relatively quickly. And then there's a creeping slope failure, which is a much slower long-term superficial slope movement characterized oftentimes by curved tree trunks, ripples on the slope surface, leaning posts, accumulation of mobilized materials on the slope. So this is great. Good to see how these things work. Let's see what they look like in real life. So big rotational failure. You can see how the material that's moved off of the slope seems to have just rotated clockwise. And this it's left our kind of a semicircular failure plane there. Next, we have a slide or a wedge failure. You can see the materials have accumulated at the bottom of the slope and left this angular failure plane on that kind of the lighter colored dry granular layer that lays over that darker, more cohesive material. A great example of how the slope failures don't necessarily happen wholesale. Like I mentioned, the layers will fail varyingly based off of their angles of repose and strength. And then we have our overhanging slope failure. Now this is it's a good shot because it's actually exhibiting what could be a couple types of slope issue. I think it may be a creeping slope based off of my understanding of the site, but it's actually a pretty clear overhanging failure waiting to happen. You can see that the toe has eroded back and the light vegetation with the fine soils on that upper layer is actually kind of holding that little layer in place. Over time or with the input of water into that upper layer, that overhanging bank is going to fall into the shoreline and the process can start back over with toe erosion. Now I mentioned that could be a creeping slope. It's hard to identify because it's hard to see on really close photos. And so we look to larger scale photos. But here's the best I could do. It's really hard to show the effects without really big scale photography. But on the left here, you can see where you've got these curving trunks of a whole stand of timber, where they're continuing to adjust vertically as the slope is moving down the hill, or I guess the surface layer is moving down the hill. In the top right, kind of a cool photo of the wrinkles that can actually form if the soil happens to be somewhat cohesive and fine and have kind of grassy materials. And then on the bottom right is the toe of a creeping slope with that angled post, which are essentially doing the same thing as the tree, but they don't adjust, so they just continue to tip over. And you can see also the accumulated materials at the bottom there. So following the order of the checklist, let's chat about water. When it comes to slope stability, water is the bad guy, the bad actor. So consider what happens when you pour a bunch of water onto the ground. It turns soupy, and it can even turn into mud and flow like water. So groundwater suspends fines, can break down the cohesive bonds that strengthen soil above its angle of repose. So water in the slope from under the ground can and will impact the stability of that slope. You can see on the photo on the left that the groundwater isn't really causing an issue, but it's certainly something you can see. However, on the photo on the right, there's a spring underneath the road here that happens to have eroded out a little blind channel. And over time, that blind channel could continue to migrate towards the road embankment and destabilize the road. So moving on, we talk about categorization. So we categorize our shorelines by some of their characteristics, and we call them shore types. So these categorizations are based off of a combination of their geology, location of a drift cell, and other things. There's a few ways to characterize beaches, and this is a place where you can kind of cheat by using things like the Washington State Coastal Atlas map, which I believe we have a link to in our links document. So these shore types, for the most part, match up with the shore types that we discuss in the guidelines. We break them down into what you see here, feeder bluff exceptional, which is on the top left there, a feeder bluff that contributes a lot of sediments regularly. Feeder bluff that provides the source of material in a drift cell, a transport zone where the reach is more regular and moves sediments in and out at about the same rate, a pocket beach where the waves approach the beach straight on and sediments stay in the system, as those headlands like I touched on last week. Artificial is referring to a shoreline that's been modified or armored, but essentially has the same geometry. An accretion shore form where sediments deposit and do not move any further in a drift cell. And then moving on, we have modified shorelines, those that have been reshaped and often do have armor. River delta, which is NAD or no appreciable drift, low energy, and bedrock. So the checklist also includes localized features aligned to keep an eye on some of those local things. Segments and small characteristics that are worth noting that may impact a design, things like glacial erratics, geometries that are unique, hummocks, wood accumulations, things like that. So then we have the note on wave climate. We refer to wave interaction at the site. Specifically for a given site, what's your maximum fetch? So fetch is defined as the open water distance that over which a wind can blow unimpeded and form waves. The easiest way to measure fetch is just by looking at an aerial map and measuring the longest distance to the nearest land. So I've included the table here that actually relates the fetch distance in Puget Sound with an energy category. A note about the energy categories, they're generally based off of a south to north wind pattern, which is how most of our prevailing winds in Puget Sound are. So if you look in the text above that table, you'll see that we actually divide the fetch value for winds from the northerly aspect in half, unless those happen to be the prevailing winds. So, and we'll touch on those categories a little bit later. So let's look at what wind and wave energy actually do to the shoreline. So along with fetch comes that drift process. So we talked about it last week. How do we observe it, or how do we tell which direction it's going? You can see it on site. You can see it with aerial photos, like what I've got here. So if you happen to be on the subject beach that you're working on, just look for something that projects vertically above the average beach and would intercept and store the sediments that are kind of moving along that beach in that drift process. The photo here is in a location that's the same location that's in the aerial, and you can see that there's a groin. That's me standing on top of that groin, and it's accumulated 3 or 4 feet of beach gravel and disrupted the gradient of that beach. Right, we've got this vertical drop now, and you can see on the aerial on the right that the beach is accreted on the updrift side of that groin and has degraded on the downdrift side of that groin. So on a more natural shoreline, things like logs and wood are great things to look for to observe that drift direction and observe kind of the drift itself. The more things that you can find that support the direction of that drift that agree with each other are good for kind of keeping that going. So let's give you guys a moment to not listen to me talk and ask you guys a question. Based off of our discussions last week and what I've run through to this point, what shore form do you think is in front of you? Might have to move the little poll form there, but I'm going to give you guys, I'll say, a minute here to think about that and chat amongst yourselves if there happens to be more than one person in the room, and I will put my answer in here, and then we'll give you guys an answer. Ah, good job. You guys nailed it. We are definitely looking at a feeder bluff exceptional. You can kind of tell mostly because of the big giant blob of material that's dropped down onto the beach, and we've got a bunch of live plants and things down on the beach there and a bunch of wood that has racked up against that. So great job. And let's do this one more time. But let's see if we can figure out which way drift is running on this photo. So an aerial and an oblique, they're the same location. One in plan view and one is the Department of Ecology oblique photo. So let's, answer me to the compass directions, and I'll give you again about a minute and see if we can all get the right answer here. All right, we got a little bit more variability here, but in this case, the drift is running from south to north. Indicators that should make that clear are all the accumulations on these groins here. You can see that on the photo on the left, the aerial, the beach sticks out further on the south end than it does on the right end, so it's accumulating sands on the south end of these groins, and the beach is somewhat degraded on the right side, on the north side of these groins. And then on the oblique there, you can actually see some of the shadows where there's no material on the downdrift side of the groins, and there's no shadows on the updrift side of the groin where material has essentially filled up that little vertical obstruction. Quick question here: how do we differentiate between a feeder bluff and a feeder bluff exceptional? Generally, you'll see, and I think I touched on this on the last webinar, but I may have missed it. But generally, on a feeder bluff exceptional, you'll almost always see that the slope is pretty much bare. There's not any vegetation, and you're seeing all those sediments because of the almost constant feeding of that bluff, as opposed to, feeding from that bluff, as opposed to a feeder bluff, which is going to have a little bit more consistent, it'll likely over time have vegetation more than a feeder bluff exceptional. You won't necessarily see quite as much material down on the beach quite as consistently. So let's move on. So as we go, we'll discuss assessing levels of risk, future slope failure, and impact to important infrastructure on the score. What better way than to document the observed flooding or erosion that's already occurring? So evidence of coastal flooding can indicate the risk of waves attacking well out of the swash zone where waves work a little bit more regularly and impacting the structures that happen to be on the backshore. So on the photo on the left there, if you squint, you can see where the high tides have left a watermark on the concrete wall, indicating that this site is probably susceptible to coastal flooding. Evidence of coastal erosion, I hope the concern, sorry to answer Allison Warner's question there, yes, I did say from south to north on the previous poll there. So anyway, for coastal erosion, I hope you guys see that if a beach or a shoreline is actively eroding, it's not going to be a reach to say that further erosion can be expected. So moving on, let's touch on beach texture and grain sizes on a beach. Generally, you want to observe that so you know if a restoration project happens to be going on or a soft shore project, you know what type of materials to put back. But what's the significance? I'll ask you to consider the difference between a Puget Sound beach and a beach on the coast. The difference between those two types of locations generally is going to be wave energy. The coast has virtually unlimited fetch, and the waves are quite high energy, whereas Puget Sound generally has shorter fetch distances and much less energy. And so, again, consider how are the beach sediments different. Here's what I think is a pretty typical Puget Sound beach. There's some sand, some gravel, a good portion of cobble, a few boulders. There's a pretty broad range of particles represented here, everything from 2 millimeters and smaller, like sands, all the way up to about the range of about 600 millimeters, like that big old boulder there. However, when you look on the open coast, we see this very consistent particle size, such as the photo in the example. You see that pretty much all the particles are in that kind of that 2 millimeter and sand size range. And hopefully you can think of other locations out on the coast where there's either all boulders or all cobbles. But generally, the particle sizes are consistent. So in a very general sense, consistent particle sizes on a beach indicate higher energy to that beach. And that's my cute little kiddo running around on the beach. I couldn't help it. So beyond the sediments and the shore proper, let's move up the beach a little bit, and we talk a little bit about the backshore and the features of that backshore. What's important to document is particularly wood, backshore vegetation. Both of these indicate healthy habitat conditions for a variety of reasons, but both also indicate some stability and relatively low energy or risk. So there may not even be a backshore in some cases, which is one of the items on the checklist there. It may be a bluff back beach, or there could be a bulkhead or another structure that happens to be on there that displaces that backshore. So these backshore features, they really ought to be described on a beach profile or a cross-section, which brings us to our next item, beach types and cross-sections. So I touched on this a little bit when talking about shore types, but project proponents should be documenting the smaller segments in the beach types, and fully documenting all of that information should include taking at least one good beach profile or cross-section. So this information, very helpful in that it shows what's there, informs how a potential future project will interact with the tides in the uplands. So the checklist has a whole list of the items that should be measured and documented on that cross-section, also oftentimes here called a beach profile. So observing the surrounding land is actually pretty simply done. In this case, it's by using aerial photography. Contours, if they're available, happen to be really helpful as well. They help you see what kind of drainage conditions you're dealing with on your site, whether that's urban, that happens to have a lot of impervious surfaces, potentially generate pollutants and more runoff. If that's farmland, which produces less runoff, but will likely come with some extra nutrients, which can bring all other issues, or natural, which creates the most favorable conditions for runoff and without pollutants or extra nutrients. So you can also kind of create expectations on how you expect the basin to change based off of spreading development. I'm a huge fan of Google Earth for doing this type of thing because it's got the built-in feature where you can go back in time. I think almost anywhere in Washington, at least, you can go back to 1994 with aerial photography, and you can see what's happened in the recent past and kind of extrapolate where that might be going. So next, what drainage controls exist on the site? Now, a lack of drainage control, poor drainage control, can potentially be the driver of shore erosion. You can see here where the concentrated flow from that grassy ditch in the parking lot is actually having pretty severe impacts on the bank that's holding the parking lot up. So anywhere is where water could concentrate and flow and potentially end up attacking a slope, or where water could be concentrated on the slope, or just areas to watch for. There could be very easily solutions to shore failures just by managing surface drainage, which we talk about in, I believe it's the next webinar, actually. So next on the list, we come to vegetation. So it may or may not be able to help prevent like large-scale mass wasting or landslides. It does function to help stabilize the slope in the interim, particularly on the timescales that we're dealing with on a lot of these mostly residential type sites. So the best vegetated slope has a broad range of vegetation types, from grasses, ground cover that can function to break up the momentum and energy of falling or flowing water, to brush that provides more of that surface level shear support, all the way up to large trees that have a little bit deeper roots to intersect failure planes, as well as aspirating moisture right up out of the slope. We talked a bit earlier about how water is the bad actor in slope stability. So well-vegetated slopes have a broad range of vegetation types, tend to be more stable than those that are non-vegetated or have a single monoculture, single type of vegetation dominating or potentially crowding out other vegetation. So I touched on vegetation. It looks like our slides may be frozen there. We seem to be stuck.
Hey, Corey, this is Sydney. I think,
Yeah.
I think Nicole and Karen might have frozen. I'm not sure if they disconnected, but that could be why we are seeing frozen slides, unfortunately.
Okay. Well, let's see here. Just gonna take a quick look at if there's any opportunity for us to jump ahead and ask a couple questions and see if people have any concerns or comments or anything like that, while we let Nicole and Karen work out what's going on their side of things. So I guess I'll open it up, unless anybody has any problem with that. Just saying, have you guys got any questions so far?
I actually had a question, Corey.
Oh, shoot. Go ahead. What do you got?
So I am wondering, as you were mentioning about the different beaches, like on the coast, what makes it being, very fine sediments versus very large sediments? I know they'll be consistent, but why is it very fine or very cobbly?
It has to do with the source. Where are your sediments coming from, and what availability is there, I guess. The best answer I have for that, that's a really good question for somebody a little bit more well experienced with coastal geomorphology. But that's my solution. Most common type of beach in Puget Sound is an accretion shore form. That's a great question. I would lean towards probably a transport zone, just because everything needs to have some way to go in and out. I can't say 100% sure. I'd have to take a look at the actual inventory of the shoreline types to see what is the most dominant type. So let's see here, another quick question. How do you determine the dominant fetch other than wind-swept trees? I'm going to answer that one real quick, and we'll put the rest of these kind of in the parking lot and come back to them because it looks like things are moving again. So how would you determine the dominant fetch? A lot of times that you'll see your drift direction is driven by that dominant fetch. Other things, the best way to check is to look at, if you have the availability, actual weather stations to see where your high winds come from and where your prevailing winds come from. And typically that will tell you the picture of exactly what your dominant fetch is. So I'm going to assume that we're moving right along. So let's move on to the next slide, whoever happens to be driving the bus there. I touched on invasives. They're particularly important to document. And really a particular concern is these plants, things like Scotch broom, blackberries, hawthorn, English ivy, butterfly bushes, things like that. So we can go ahead and cycle forward one more time on that slide. So these plants are kind of not cool because they aggressively crowd out natural vegetation, but they're particularly harmful to just the stability of that slope. They tend to be so successful because they grow aggressively. They have really shallow roots that spread really quickly and intercept rainwater, but actually do very little to hold a slope in place, especially at those deeper failure planes where more naturally, potentially deeper rooted plants can work. Oh boy. So I'm going to keep going. So they'll actually crowd out the naturally deep-rooted things, particularly on a newly cleared slope. Should geotechnical, got a question there, should geotechnical consultants use the checklist? I'm going to answer that one because it's a real easy one. Yes, they should. And actually Sydney's going to address a way for you or anyone else to assess the information that you get on that geotechnical report. So at this point, we've characterized the natural setting of the beach. Let's turn to the developments on the site. This is particularly important when we go to make a determination of risk, which we'll talk about a little bit later. The information needs to be clarified, as well as where, like what it is, what type of structure happens to be there, and where it sits in relation to the top or toe of a bluff. So to paint the picture of how much in danger it's going to be, and the importance of that structure. What is it? How important is it that that is protected? So moving on, we have our line item next on cultural resources. Can I get a slide advance there?
Sorry, folks, we're
Sounds
just
like
having a little bit more technical difficulty. We're really sorry about this.
Okay, well, since we got a moment here, I'm going to go ahead and grab onto a couple of these other questions. Let's see here. From Lauren. Oh, real quick, I'll hit on Lauren's question here. So if it is an expectation that habitat bios will be filling out the checklist when they do their site visits, not necessarily. So the checklist was actually developed specifically for a design audience. So it's got a lot of things that aren't necessarily 100% pertinent to a reviewer. And that's why some of these items that we're running through, I'm going relatively quickly through. But I'd say use it less as some sort of a requirement and more as something, a tool to help potentially lead you in the directions that should be dictating what you get out of a project. So use it at your own discretion is the best way I can say that. So looks like things move forward. So I'm going to be kind of brief on cultural resources because it doesn't actually have anything to do necessarily with what's appropriate from a slope stability perspective, but really it oftentimes does change what's appropriate based off of what happens to be in the slope. or on the beach. So moving forward, other than the things that should be obvious, like human remains and things like tools or pottery, arrowheads, there are less obvious items to be on the lookout, particularly things like fire-cracked rock and shell midden. So on the left there, some fire-cracked rock. I hope it's pretty self-descriptive. It's rocks that have been cracked by fire. Particularly if it's in a large quantity and if it's not fresh. So if you see fire-cracked rock that has barnacles or algae or looks weathered, means that it indicates past occupation that has subsequently had some weathering or time on top of it. So, and then on the right there is a photo of some shell midden, a pile of shells. They're all stacked in a way that indicates they were placed there during some regular occupation. Really, it's a matter of where a whole bunch of shells were chucked out after they were shucked. Clams or oysters, when they happen to be piled up, they all will kind of land in a similar pile. Sorry, they will land in a similar orientation in a pile, as opposed to if they were tossed around by the beach, where they would get a little bit more beat up and be less solid pieces. So oftentimes these items and things that will be on a site will justify hard armor where other conditions don't. So erosion control structures, really it's very much something that should be incorporated into design, but as a reviewer, it's something that can indicate past erosion problems. So erosion control devices need to be documented. You can see on the left what looks to be a temporary straw wattle there in the photo, and on the right a more permanent thing like a drain pipe. So these devices may indicate that a problem has been and is currently ongoing. So next we have our last section of the checklist, which is determining site-based causes of erosion. This really falls to a project proponent or their agent to identify and explain to the planner or permit reviewer. Really, the information that we've covered so far should be helping to inform this determination. And we've got more tools in the guidelines that will help describe and make this available to you. And actually, Sydney's going to talk a little bit about that as well. So this figure here, straight out of Chapter 3 in the guidelines, and describes the common causes that might help make that determination of site-based causes. And this is the last item on the checklist. So I'm actually going to hand it off to Sydney next and let her talk about demonstration of need.
Thanks, Corey, for that overview of site assessments. And again, really sorry everyone for the technical difficulties. We are doing our best, so thank you for your patience. We'll be going back to Corey in just a moment, but first we want to highlight some regulatory elements and really drive home that connection between these technical site assessments and the permit review. So Corey just talked about those technical elements of a geotechnical report and what to keep your eye out for when reviewing those reports. Now let's tie those considerations back to SMPs and the demonstration of need and highlight a tool that we've provided for you for evaluating geotechnical reports. There we go, there's a graphic, and this is a great graphic that I like to use to highlight the mitigation sequence found in comprehensively updated shoreline master programs for shoreline projects. And this is for all projects, whether they're bulkheads, docks, you name it. Following this sequence is the key to achieving no net loss of ecological functions. So first we aim to avoid that impact, then minimize the impact through design options, and finally compensate for any unavoidable impacts. And today we're going to be focusing on avoidance, and we'll also revisit this graphic in the next webinar. In terms of shoreline stabilization, the idea is to avoid unnecessary bulkheads. Avoidance for new development can be achieved by locating that new development so it won't need any protection in the future. And for existing structures, avoidance can be achieved by demonstrating that the shoreline stabilization is needed at the site. Corey's just gone through some of the key technical or site-specific elements that help define the level of risk at a site. What Corey was just describing about site assessment forms the basis of a demonstration of need. So basically, if site characteristics don't indicate that there's erosion threatening a structure, there isn't a need for stabilization, and that shoreline construction impact can be avoided. We also want to note that WDFW's HPA approval process also uses a mitigation sequence. Habitat biologists issuing HPAs are looking to evaluate first the immediate construction impacts to fish and also the long-term impacts that a structure can cause. So through technical assistance and conditioning permits, the HPA also works to avoid, minimize, and compensate for impacts to resources. Avoidance of unnecessary bulkheads is called out in Ecology's SMP guidelines, which are WAC 173.26.231, Washington Administrative Code. So any jurisdiction with a comprehensively updated SMP has this language in their code. So this is just a reminder of how the regulatory provisions relate to the technical discussion we just heard from Corey. So I'm going to walk through a number of key points to remember about the WAC. And so some of the key points related to avoidance first are that new development should be located and designed to avoid the need for future shoreline stabilization. Basically, new development should be built so it won't need stabilization down the line. Second, new or enlarged stabilization to protect primary structures necessitates that there be a demonstrated need for that in a geotechnical analysis. In other words, application for new or enlarged shoreline stabilization requires that the need to protect a primary structure be documented in a geotechnical report. Third, and very importantly, the danger must be from erosion caused by currents, tides, or waves. So the hazard must be caused by things actually happening on the shoreline. Upland issues, such as drainage, are not sufficient to justify stabilization. And as Corey was explaining, stabilization is not the correct tool to address those issues. Fourth, you need a geotechnical report that estimates timeframes and rates of erosion in order to estimate when a primary structure will be damaged. So generally, hard armor can be authorized when there is a risk to the structure within 3 years. Note that if the geotechnical analysis finds that the structure is at risk at some later date beyond 3 years, that report can still be used to justify soft-shore protection. One of the tools that we've created is a checklist to assist with review of geotechnical reports. This document is available as part of your handout packet that you can download either from your reminder email or from the Coastal Planners Group website. This geotechnical report checklist, which you can see here, walks a reviewer through the technical questions that the report needs to be addressing. So this checklist can help planners and permit reviewers by identifying the types of technical information that should be found in a satisfactory geotechnical report. The checklist walks through several questions to identify if key information is present in the report. So questions that it asks include, is there evidence for active erosion on the slope? Does the site have a history of landslides? What is the shore type and drift direction? And is there water on the site? So they should be sounding familiar based on what Corey was just going through. And the second page continues along these lines. Does the report answer things like, what are the subsurface conditions? So asking about the soils. What are the structures on the site? Are they close to the shoreline? Is erosion and wave action driving the slope instability, or is it from an upland issue? And how fast is erosion happening, and when will that impact the structures on the site? So hopefully these questions are sounding like they're shaping a demonstration of need assessment that the WAC outlines. So things like erosion rates, causes of erosion, and when that erosion might put structures at risk. And it should also be sounding familiar to what Corey was talking about. And just one more quick thing, a note about replacements. So as we covered in the previous webinar, replacements are very, very common. I don't think that comes as a surprise to anybody listening. And according to the WAC, replacements also require a demonstrated need. And so those questions that were asked in the geotechnical report checklist would certainly apply to considerations of whether continued stabilization is needed at a site. However, as we mentioned in webinar 1, a geotechnical report is not required for replacements by the WAC. Now, some jurisdictions' SMPs do require that geotechnical report for replacements, but regardless of whether a a geotechnical report is required by the SMP for replacements, the questions raised in the checklist are useful to get at demonstration of need, however you're evaluating it, whether it's by reviewing photos of the site or visiting the site in person. And if you would like more information about this topic, we recommend viewing Chapter 15 of Ecology's SMP Handbook for more information. Again, a link to that is on the Coastal Planners Group website. Now, Corey's going to show us another tool that you can use that we've provided, and this one's for assessing cumulative risk at a site, which again feeds right into the need for stabilization at the site. And it looks like we had a quick question, and Corey's covered it in the chat, so I'll just pass it over to Corey.
Yep, so hopefully that's a good enough answer there. We're going to talk about techniques next week, where we actually will discuss what we call passive techniques, which are discussed in Chapter 6 of the guidelines. So let's move on to risk. In lieu of demonstration of need, the guidelines are more specific to the design audience. And so we describe a technique for assessing the level of risk at a site. The way we do that is using what we call the cumulative risk model. So here's what that model looks like. It also is in your handout packet and in the guidelines. This is calibrated and refined using data from the study of 25 sites that was the building blocks for the guidelines themselves, with a little bit of additional unpublished data and some data from Hugh Shipman. So the model doesn't necessarily quantify the risk of slope failure, though that is a component of it. So rather, the model breaks the risk into 4 specific categories. What is the risk of slope failure based on the shore type? What's the risk of slope failure based off of wave energetics? What is the risk based off of the object, where the object of concern is located in relation to the slope or the beach? And what is the risk based off of what that structure is? So the categories then get binned into two other subcategories, I guess you could say: erosion potential, or the risk of the slope failing, and then infrastructure threat. What's the risk of damage as a result of that slope failure? So consider if there's a high slope on the shoreline and it's susceptible to failure, and there's no infrastructure on that property at the top of the bluff, is that really a risky location? So that's the purpose of breaking those aspects out. Starting with the shore type, that's information right out of the site assessment that we discussed earlier. Does the shore that your subject site is on have a likelihood to be unstable? Bedrock? Probably not. River delta? Probably not. A bluff? Yeah, and probably, and then a feeder bluff? Unequivocally, yes. Sorry, did I say feeder bluff exceptional there? Unequivocally, yes. There we go. Got off my script a little bit. So the shore types that are listed on the table itself, they're all based off of the CGS, the Coastal Geologic Services framework. But any other shore type, things like Shipman's shore types or another framework could work, as long as the likelihood of slope instability can kind of be gleaned from the description and fit into the scores here. So once you've got your shore type score, you move on to the wave energy section here. And this is pretty straightforward. If you've got any experience measuring fetch and checking prevailing winds directions. So in the previous module, we touched on measuring fetch. We did it a little bit earlier and what that means as far as wave energy. And we do the same reduction here in fetch for winds from the northern quadrants, unless that happens to be the prevailing winds direction. So to further clarify the categories, they're based off of studies in Puget Sound and Japan that have documented the wave heights that will drive, that will cause bluff movement, and the fetch distances associated with those wave heights. So bluffs don't really see mobility from waves until the waves reach about a couple feet tall. And that wave energy will actually increase fourfold for waves that are just twice as tall. So for the wind conditions in bathymetric setting we've got in Puget Sound, we see about a 2-foot tall wave forming at about a mile of prevailing wind fetch. And a 4-foot wave at about 5 miles of fetch, and kind of on up from there. So the categories here, they also match the FEMA risk zones for coastal flooding maps. So pretty consistent there. And from there, we do pretty simple math of adding the shore type score and our fetch score to get what we'll call the erosion potential score. So moving quickly on, we get to our setback score. So from your site geometry observations, how far is your structure set back from the top of the slope, if you happen to be in a bluff or a low bank site, or from the ordinary high water and no bank site? So find the corresponding score from the infrastructure setback portion of the table. Ought to be pretty logical that the closer your structure is to the active portion of a slope or beach, the higher that risk will be to that structure. So when you're looking at the scores, you'll see they go up for lower setback distances. And then our last category here is infrastructure type. So note on infrastructure type, loosely based off of an importance factor that engineers usually use in structural applications, which happens to be ASCE 07 if you're curious. We get to do the impersonal job of assigning more importance to structures that have larger implications of failure. So consider something like a school or a hospital more important than a barn. So the same thing is kind of what drives this. If a major infrastructure fails, we impact a lot of people, whereas if property without structure fails, we impact no one directly. So to tell the story of the photos here, the picture on the left here, there's an 8-inch high pressure water main, less than a foot horizontally from that exposed brick face that you see. So if that were to be exposed and fail, we have a couple hundred homes with either no water or contaminated water, as opposed to the photo on the right, where you can see there's a little boathouse that's very close to the bulkhead. It's on the verge of failing and was failing in places, but it's not occupied, so it gets a relatively low importance score. Now back to the big guy there. We select our infrastructure type, we add that to our setback score, and the last job is to multiply the erosion potential score and the infrastructure threat score, and gives us a cumulative risk total, which we then use to categorize our level of risk, which you can see on the little table at the bottom, at the bottom of the table there. And so we'll use that information as we roll into the next section and what we'll talk about in the next webinar, which is alternatives analysis and appropriate techniques. So let's walk through a couple quick examples and get an idea of how these factors actually function. So here's a WDFW access property in Hood Canal, a very northward edge of Dabob Bay, I believe, or up in the northern side there. It's called Indian John. You can see that we've got a relatively low energy area. So knowing our shore type score, we measure fetch. In this case, it happens to be just over a mile, and we get a 0 for shore type score because it's low energy, and we get a 2 for our fetch score. We add those together, and we get an erosion potential of 2. So I'm going to give the answers here to the infrastructure section. There's basically no offset from the top of the slope to the back of the parking lot, but it's an unoccupied space without any structures. So we select a 4 for the setback score and a 1 for the infrastructure type score, and adding, we get a 5, and then we multiply to get our total risk of 10, which indicates a low risk site, well within that low risk section. So for contrast, let's look at a site here. For the site we're going to look at is the shoreline at Potlatch State Park, or just northward of that, on Hood Canal near Hoodsport. To the left of the photo here is a parking lot. There's water line, septic facility, and that's the infrastructure that we're going to use. Let's see here, we've got a question. Any consideration of sea level rise in this analysis? Not for the risk assessment as it stands now, but we're actually going to talk about sea level rise in a couple of weeks. And it's probably something that will get incorporated in future and subsequent updates. So thank you for the question. So at this site, we happen to be at a accretion shore form. But just updrift of that is a, let's see here, there's a transport zone. And so let's use that score for demonstration purposes. You can see the measured fetch is pretty far, about 12 miles from the north by northeast. And a review of the weather station at Potlatch State Park shows us that this is actually our prevailing winds direction. So we take that fetch number at face value instead of dividing it by 2. Interesting to note, it wouldn't have mattered, we'd be in the same category. But if you follow the table on the right up there, we'll call this major infrastructure for demonstration purposes again, and we end up with a score that indicates a high risk, right? We get a 2 and a 3 for our erosion potential for a cumulative of 5, We get a 4 and a 4 for our infrastructure threat, which gives us an 8. Multiplied together, we get a 40, which puts us just outside of the moderate risk and into the high risk zone there. So again, that drives our appropriate techniques, and which we'll be talking about next week.
Excellent. Thank you, Corey, for that overview. Now we're going to open it up for some questions. So as you're thinking about your questions, please go ahead and type them in the chat box. We'll try to answer them in the order that they come in. But before we get to those, and while you're thinking, we do want to remind you about our next webinar coming up. So webinar 3 in our series is going to be held next Tuesday, the same start time of 9:30 a.m. And it is going to cover the range of shoreline techniques and how to determine which shoreline treatment is most appropriate for the site conditions and the level of risk at the site. If you're not registered for webinar 3 or webinar 4, which Corey just plugged about sea level rise, we encourage you to visit our website, coastalplanners.org/webinars, and register for each. And again, recordings and slideshows of these webinars are going to be posted on the website as well. So now let's go ahead and take a look at the questions. I'll grab the ones that are coming in first, and then if time permits, I'll go back up in the chat and get the ones that were posted in earlier when you all were being very patient as we dealt with the technical issues. So let's take a look at the question from Hannah. What types of roads, if any, are considered to be major infrastructure for this assessment? That sounds like a question for Corey.
Yeah, that's probably going to be any road. I would, especially if it happens to be well used. There's probably a justification for a road being considered less major infrastructure if it happens to be seasonal use, gravel road with no infrastructure, no water lines, no sewer lines, no electrical, things like that other people rely on. So there's a little bit of objectivity in how that gets determined. Any road that's well used or frequently used would be considered major infrastructure. And actually, I'm going to jump back. There's one question that that was up above from when we had the issues earlier that I wanted to address. I want to make sure it didn't get missed. It was from Allison Warner, and the question was larger grain size. Does larger grain size indicate higher energy? Similar to how, or is it the opposite of the way you see things in a fluvial or a freshwater system where larger particles are indicative of higher energy? That's not necessarily the case where we're talking in the shoreline. Consider that we get energy from 2 different directions on the shoreline. We don't necessarily just have flowing water. We have flowing water as waves recede and also water as waves approach. And so those waves will pick up and throw all of the finer particles like the sands, which is why we also see high energy locations with sands and smaller particles like the open coastline, right? If you go out on Long Beach, that is a very high energy location and it's a very fine beach. So the size of the particle doesn't always necessarily indicate the energy that happens to be on that beach. It has more to do with the let me make sure I state this correctly. It has more to do with the range of particle sizes to indicate the energy at a beach.
Great. And Corey, more questions for you. Who is qualified to perform a shoreline risk assessment? And I'll piggyback on that. Should habitat biologists be filling out the checklist, the site assessment checklist, when they do their site visits? So who should be doing this, and are habitat bios expected to do something like that?
I wouldn't say that they're necessarily expected to, but I would expect that they certainly could. Really, anyone's qualified, I guess, to use the site assessment and really even the risk assessment. And as long as it kind of informs your understanding of what's going on the site and gives you that level of comfort. And so for somebody like a habitat biologist or a planner, you could use that to kind of back check what you're seeing as far as a proposal, and which could dictate and derive how you respond to that proposal. So somebody proposes a bulkhead in a very low energy location with no structures, you could run through the site assessment and or the risk assessment. Say, hey, this doesn't really pan out. I guess in my ideal world, I would see people filling all this out and submitting that with an application. So you could say, hey, look, they've done the work. Let me run through and double check a few things. Okay, we agree, and move on.
Excellent, thank you. Another question for you. I guess we anticipated that you'd be getting the bulk of the questions because you were doing the heavy lift on this webinar. Is the setback that's used to calculate erosion risk the allowed setback for the site, or the actual distance that the structure is set back from the ordinary high water mark?
So that's the actual distance that you see from the either the high water mark if you happen to be in a non-slope or bluff location, or just the distance from the top, or did I say top or toe? I don't remember exactly what the language is, but essentially from the dynamic portion of that slope, so probably the top of the slope, what's that setback distance? It's not necessarily the allowed setback, it's going to be what physically is on the site.
Great.
And I guess I'll just keep going if that's all right.
Yeah, sure. The next one's definitely for you. I think the one after might be for me, but I'll let you take the next one.
Yes. Yep, I'll take that next one. So does wind direction dampen or heighten the fetch calculation? For instance, at Potlatch State Park. So wind direction would tell you which, let me just make sure I describe this the right way. The direction that is the prevailing wind's direction will let you know if that is the worst case fetch scenario. So if you have a few miles of fetch one direction, but you've got 20 miles of fetch from the other direction, but all of your winds come from that 2 mile fetch direction, that's really what ought to be driving, unless you happen to see some seasonal changes where you get some of your big high winds from that 20 mile fetch direction, in which case you would use that. So the wind direction really just tells you, it'll qualify if you have a couple different fetches from the north, one from the north and one from the south, that are really relatively similar or different enough that they would drive you into a different energy situation for the wave energy categories that drive that risk assessment.
Great, thanks. The next question I believe is for me. Does ecology still require level risk assessment for replacement? So if I understand the question correctly, basically, should these ideas of risk be coming into consideration for replacement? And I would say the answer to that question is yes. So if you think about what it says in WAC 173.26.231, replacements are authorized if there is a demonstrated need. And so while that demonstrated need is not required to be shown through a geotechnical report, at least according to ecology standards, local SMPs may vary, you still have to think about, is there a need for the continued stabilization or a continued structure to exist at that site? And I think really what the question about risk assessment is driving at is there a risk at that site and what can you do about it? And so, yes, in the sense of trying to answer, is there a structure that could be damaged by erosion? What is the potential for that erosion under the time frame of interest? And what is the source of that potential hazard? Is it upland versus, shoreline-based erosion caused by tides, waves, or currents? Yes, the replacement does require that risk assessment. And hopefully the materials that we provided today could walk you through that, regardless of whether you're evaluating a geotechnical report for a replacement, or even just looking at photos or driving out to the site and seeing it, in the sense that assessing risk, you could see from photos, for example, wow, that home is actually really close to the shoreline, or wow, we know there's a septic system there. That would be something that would qualify as, yes, there is a need for that replacement under today's standards of review, versus, for example, a situation where, let's say the bulkhead was built in the 1960s before these things were regulated. The house is actually set back 60 feet from the shoreline. It's a low energy wave environment. That bulkhead does not necessarily need to be there anymore. And so that would be the risk that you would be trying to assess for that replacement. Next question, Corey, maybe you know the answer to this. Has there been any legal challenge to the model based on the weight it gives to sites that have structures versus sites with raw land, i.e. a challenge based on reduction to property value should erosion occur?
I do not know that that has been challenged at all. I know that there's been some a little bit of legal action on more on the county side of things, specifically as it relates to what constitutes a risk to structures based off of the timeline that happens to be in that county's code. Pretty commonly 3 years, risk to the structure in 3 years. Can you demonstrate it? Then we'll move you into the making that acceptable. So I know that there's been some legal challenges in that world. I don't know that there has been with the guidelines, and I hope that there's not, I guess, but it wouldn't surprise me if that would happen, especially considering, like you say, the reductions to property values should erosion occur, and the potential, which we'll touch on again in 2 weeks, on how that might be further manifested with sea level rise considerations. So it wouldn't surprise me at all, and it's probably something that hopefully someone's preparing for, and I guess we probably ought to have it somewhat teased out a little bit in the guidelines. But no, not that I'm aware of. I don't know that our model has been challenged. And actually, I'll just grab onto this next one here too. When a small segment of beach is restored, abutting shorelines, when a small segment of beach is restored and abutting shorelines remain unarmored, what considerations need to be factored to avoid those erosional forces from adjacent armored shorelines? What's pretty common is seeing those end effects, is what I assume you're kind of talking about. And those are described in the guidelines in Chapter 4. In the process assessment, I believe, is where they discuss that. Actually, no, it may be in Chapter 3 where I actually showed the table there. But what commonly happens is people will put a return on what's left of the bulkhead that happens to be remaining, and it tends to be, in my experience, it's more protective to that bulkhead, because as long as restoration is done on the right sites, usually some mobility of that slope or that shoreline is acceptable, because that's what we want to have restored. More commonly is the issue of what happens to the end of my neighbor's bulkheads when I take mine out and let my beach move. And so a lot of times we'll see people will be putting what's called a return. They'll essentially wrap the edge of a bulkhead or a revetment around, so that there's a place for that wave energy from the wave kind of wrapping around the face of that structure, a place for that to be manifested so it doesn't attack just a raw slope. So usually you'll see returns, and that's actually discussed in the guidelines as well. So, and then I think I'll let Sydney answer the question from Laura there. It looks like it was probably in response to what she was just discussing.
Yep, that's for me. So the question is, what about repair? Is the geotechnical assessment required? So generally, the answer to that is going to be no. Repairs generally get viewed by local governments as that normal repair and maintenance, don't require a geotechnical assessment. And probably most likely, again, depending on the scale of the repair, you know, if you're just talking about replacing a couple boards or filling a crack in a concrete wall, that's at a much different scale and a much different level of scrutiny than, say, replacing 50% of a wall or 60% of a wall or replacing an entire wall. And that actually, as I'm saying that, it reminds me, it's important to remember there's more variability on what local governments, SMPs, say about repairs and replacements than there is about new or enlarged structures. So as I was covering in the slides, new or enlarged shoreline stabilization, it requires that geotechnical report. It requires that demonstration of need that has to be shown through a geotechnical assessment. Whereas, as I was mentioning with replacements, does not necessarily require a geotechnical report. Local governments may require it. And then also there is some variability at the local level of what constitutes a repair versus a replacement. So some jurisdictions will say, you know, if you're replacing more than 50% of the structure, that's going, or if you're redoing, I should say, if you're working on more than 50% of the structure, that's jumping from a repair to a replacement, and there might be more scrutiny. But again, that varies by local government. So if you're in a local government or you are working with local governments, make sure you check their SMP for not only what constitutes a replacement, but then also how that need for the replacement should be demonstrated. But for repairs, generally that's kind of viewed as a lower scale and doesn't rise to the same level of scrutiny. Looks like we've got another question coming in. And so folks, again, reminder, if you have questions, go ahead and send them in. Otherwise, we'll be wrapping up soon and definitely wrapping up by 11, which is the time that we have allotted. But we have a question from Harriet saying, I wonder if uniformity of sediment size is always indicative of high energy. Mudflats have uniform sediment size, but are usually low energy. Also here on East Coast Vancouver Island, many beaches contain sand to boulders, and this varies seasonally, but given fetches of 10 plus miles are pretty high energy. So Corey, I think that sounds like a comment or question or a response from you.
Yes, absolutely. I absolutely agree with what you're describing, specifically when it relates to mudflats or estuarine locations, which tend to be very low energy, but have that very, what we would call poorly graded VIX. So yes, the rule is very much general. And if for context, I guess mentioning the East Coast Vancouver Island, relatively high energy, specifically for like our setting in the Salish Sea, I guess we're talking about the entirety of our zone here. But I guess I would point more towards areas that have hundreds and thousands of miles of fetch, where the waves have gained all the energy that they can. We do tend to see those more consistent. So looking out towards more outer coast beaches, we do tend to see more consistent sediment sizes. But again, it's very much a general rule. It has also to do a lot with what is your sediment source, what's available. If there's no gravel available to work through the system, then you're probably not going to see gravel on the beach. So it is a very general rule, and when it comes to the context, I guess in the checklist is more. Sorry, I would say this. More to document what's there. So if and when a project occurs, whether that's restoration offshore or some sort of structural project, what needs to go back in. So yeah, exactly. It's a very much a general rule, but also there's a lot of cases where that's not necessarily spot on, specifically mudflats. So thank you.
Great, so I'm not seeing any more activity in the chat box. So I think we'll go ahead and wrap it up. So I want to say a big thank you again, everyone, for joining us today. Thank you for your great questions. And we hope to see you again next week for webinar 3, which is going to cover, again, the range of different shoreline techniques. So passive, soft shore, and hard armoring, and how to determine which of those treatments is most appropriate for the site conditions and for the level of risk at the site. Again, if you want to register, and we hope that you will join us, you can do that at coastalplanners.org/webinars for webinar 3 and webinar 4. You can also find our materials, find a list of helpful links, and also recordings of the webinars and slides with notes on our website. So thank you again. Oh, and a reminder from Nicole, if you've been listening as a group, I know we've got some folks who are in a room and it's showing up as one person, but there's actually 5 or 6 of you there in the room potentially. If you could just email us, Nicole's email address is there in the chat, fagan@uw.edu. So we can stay in touch and also get an accurate count of how many folks attended. It's really helpful for us to know if this format is useful and if we want to continue to deliver trainings and information like this in the future. And again, speaking of format, thanks again, everyone, for your patience with the technical issues, and we hope to see you again next week.